The next talk will be presented by Fischer and colleagues, and this is joint work between IAS 6 and INM 10 at the Research Center in Jülich, RWTH Aachen University, and the Hebrew University. The title of the talk is Critical Feature Learning in Deep Neural Networks. So we are looking forward to your talk.
Yeah, I think we're still waiting for the slides. Okay. Yeah, thanks so much for giving me the opportunity to present our recent work called Critical Feature Learning in Deep Neural Networks here. All right, so this will be a bit more technical talk, but I'll try to walk you through what's relevant. Okay, so when it comes to describing neural networks theoretically, there are two main regimes that people consider. One is the so-called lazy learning regime, where the network parameters change only slightly from their initial values during training. And this is already quite well understood in terms of concepts like the neural network Gaussian process kernel and the neural tangent kernel. And the other regime is the so-called feature learning regime, where now network parameters change strongly compared to their initial values, and therefore we expect the network to, in some sense, learn the features of the task that it's given. And the main difference between, or one of the main differences between these two regimes is also that networks in this feature learning regime typically show better performance than in the lazy learning regime. And here there are still many open questions, and if you want some other perspectives on this, there are also these other references here. And before I tell you about our approach, let me talk a bit more about this neural network Gaussian process kernel, because this is what we will use as a baseline later. Okay, so this is our setup. We look at a feed-forward network with L layers, and now we assume that there's a Gaussian prior on the network weights at initialization. And then on top, we have a training data set of P data samples with inputs X and labels Y. And now when we take the network width n to infinity, what we get is the so-called neural network Gaussian process kernel. And so basically, where this comes from is we look at the signal age in every layer, and there we have the linear operation, and now we have a sum of a lot of different IRD variables, and then from the central limit theorem, you get that the signal here becomes Gaussian distributed. And now this distribution comes from the distribution of the network weights. That's basically for all of these inputs X alpha. And now to describe the joint distribution of all of the training data inputs, what you also need is the so-called network kernel, which gives you the covariance between the different inputs X alpha and X beta. Okay, and now to compute or to determine this, basically you start with the inputs and compute the so-called input kernel that consists of the overlaps between different inputs X alpha and X beta, and then you propagate this through the network over all the layers according, like by computing these Gaussian averages here. And now what's missing here essentially is the information about the network labels, but this is in that sense only like a naive prior that only knows about the network inputs, and therefore doesn't know anything about the input-output relation that we would actually like to learn. Okay, and now this is exactly what we would like to understand better, and for this, to describe this now in a feature learning setting, we consider the so-called proportional limit. Now here we don't only take the network width n to infinity, but also the number of training samples p, and keeping the ratio between them fixed and non-zero, which then means that basically the load on the network is non-zero. Okay, and in contrast to what people usually do in practice, we don't train our networks with an algorithm like SGD or ADAM, but what we're interested in is the so-called Bayesian network posterior. And now what this means is so we've assumed that there's a Gaussian prior on the network weights, and then basically we can now sample different network realizations from this network prior that have different connectivities, which then give us from the Gaussian prior on the weights the network prior. And then now we only select from these network realizations those that actually already implement the correct input-output relation between inputs X and labels Y. Okay, Now to get the Bayesian network posterior, we start actually by computing the network prior. And this basically we do by computing the distribution of the network outputs by taking the average over the network parameters theta. And when doing so, what appears as a natural order parameters are what I call here some kind of generalized kernel, and then this allows us to write the network prior purely in like a kernel view, where now the network prior is given as a superposition as Gaussian. So we have here the Gaussian with the kernel C, and now these kernel C are themselves again distributed according to some distribution which I can we write this down here so nicely because it gives us this nice interpretation as a superposition of Gaussians, but it's actually not analytically tractable. Okay, and now this particular distribution of the kernels can actually depend on the hyperparameters of the network. So basically, it can consist of more different kernels, like here down below, giving us more flexibility. Because now in this, if we go again to this Bayesian picture, what conditioning on the training labels means is that that from all of these kernels that we have, we take those that implement the correct input-output mapping. And yeah, and then if we take those kernels in the posterior that do this, we can have a distribution of kernels, which is always difficult to describe. So instead, what we look at is the most likely value of these kernels, or the so-called maximum a posteriori kernel. And now I will skip the derivation, but directly go to the result. So what we get for these kernels now is a set of forward-backward propagation equations. And for the forward equations, we actually have two terms for the kernel C. So the first term here has the same structure, essentially, as the neural network Gaussian process kernel that I've shown you before. And now we, in addition, here get a correction term on top of this, this first term that consists of two terms. The first term is a four-point term that describes the interaction of the different samples. And the second term are now these tilde C variables, which basically describe how the information about the labels is propagated in the network, or more in terms of here equations like the C tilde in layer L describes how the kernel in the next layer actually depends on the kernel in the previous layer. And to make this, put this in the same picture that we had for the NNGP, we again have the same initial condition of the input overlaps. Then this is being forward propagated now with a slightly different mapping here. And now in addition, we get a final condition that measures how the log likelihood of the labels under the kernel is dependent basically on this choice of the kernel. And then and this can also then be kind of seen like as an error measure between the kernel that we currently have and the kernel YY transpose that we're trying to map to. And then this information is again propagated, and most importantly here we have an interaction between these two equations. Yeah, and basically due to this interaction, what we can describe is this input-output relation between inputs X and outputs labels Y that we want to capture. Okay, now that we have this in terms of equation, let's look into how this looks in practice. And the task we first look at is the formulation of the XOR task that's given as a Gaussian mixture here, where the two red Gaussian blobs correspond to one class and the two yellow Gaussian blobs correspond to one class. Now I show you first the input kernel, which doesn't have much structure in the beginning. And now what we want the network to learn in terms of this kernel view is the target kernel here on the right. That's basically given by the outer product of the labels, but the most important feature of this is this block structure, because this block structure is what ensures then that the network correctly discriminates between the two classes. And now on top, I show you what the NNGP looks across layers. And there basically the only thing that mainly changes is the scale. So there's no block structure that is being learned by the network because it doesn't have any information about the labels a priori. And then here down, I show you the feature-corrected kernels that we compute here in this work. where you can see how slowly this block structure emerges over layers. Okay, and now to make this more quantitative, we compute the so-called kernel target alignment between the output kernel, so the last kernel here, and the target kernel, which basically measures like how much is this block structure present here in the feature-corrected kernels. Okay, and now we plot this always, so I plot here what I call the delta CK, so that's always relative to the NNGP, which is the naive kernel that we take as a baseline. You can see that for different rate variances, this already matches quite well. And we also show how this behaves as a function of this load value, this ratio between the number of data samples and the network width. So basically, if I increase the network width, thereby decreasing my load, the corrections I get become smaller. And vice versa, if I increase the number of data samples by keeping my network width fixed, I increase the load, and therefore also my corrections here increase relative to the NNGP. Okay, now one important thing to note is here that we actually don't put any constraint on the input data. All we need is this overlap input kernel. And so we can also do this, apply this framework to other tasks such as MNIST. So here we do classification between the digits 0 and 3. And now on the level of the kernels, again, we see how this block structure emerges across layers. And here, again, I show the cosine, like this kernel target alignment for different values of the weight variance. And here, we have a quite good qualitative match. And you can see, again, that there's a big, we get significant corrections here relative to the NNGP, which is given by this gray baseline. And now what's interesting is here is that there seems to be a value as a function of the rate variance where this alignment becomes optimal in some sense, and this is what we wanted to understand better. And for this, we took a closer look at the expressions for the tilde-c variables, and basically see that these consist of two terms. So the first, or the second term actually, is this expression here to the second, like this product here, which is the so-called backward response. And this was already discussed in Schönhaus et al. From 2017. So basically what this measures is how the gradient signal propagates backward through the network across layers. And what they show is that this backward response shows an exponential decay over layers that can be described by this depth scale Xi here. And for particular values of this weight variance, this depth scale actually shows a divergence, which is at the transition to chaos, basically, when the network first is in a state where all inputs correlates, and then transitions to a state where all signals decorrelate. And they say networks only at initialization, and the conclusion was that initializing networks at this transition to chaos is beneficial for training because then these curves here essentially become flat, and the signal can propagate backwards to very, very deep layers. Okay, now we actually have a second term appearing here, which is the C tilde in the last layer, where I said before that this can be seen as an error measure between what the kernel C is and what this target kernel should be. And now if we actually put these two together, so here first by plotting the gradient signal itself, we see that it's now not the flattest curve anymore that gives the biggest signal here in the input, but it actually depends also on where you start from, basically what this error signal is in the beginning. And this error signal again also depends on the hyperparameters such as the weight variance. So there's a trade-off between the two which we plot here. So this dashed line is this error signal, which becomes big for very small weight variances. And then the dotted line is the result you get from the backward response. And then we see that basically the value where we get optimal alignment now slightly lower than this critical value that was found by Schönholz et al. Because of this interplay that we have between this error measure and the backward response. All right, and with this, I already come to my conclusion. So basically, maybe the main takeaways is that there are these two regimes. One is the lazy learning regime, and one is the feature learning regime. And now here we present an approach to understand what happens in neural networks in the feature learning regime, where we derive expressions for these maximum a posteriori kernels, and see actually that there's a nonlinear kernel adaptation in neural networks. And more interestingly, we find that there's a trade-off between being close to this transition to chaos, or also called criticality, and the output scale of the network, leading to different optimal values for optimal kernel target alignment. Yeah, and if you're interested in more of the details, there's also a preprint out, and yeah.
So thank you very much for your talk. Are there any questions from the audience? So while people are getting closer to the microphones, a question from my side. This Gaussian process-based approach that you set up, how large are the networks that you can analyze with this in practice? And what is the more prominent limitation? Is it the number of neurons or the number of training examples?
So we can actually go down to rather narrow, so like two networks of like width 1,000 or 500. We kind of use a trick here. So basically, for this approximation I've showed, we use that the corrections are small compared to the energy p. But then actually, to solve these equations, we go from very large network and basically iteratively compute corrections, which allows us to go down to much more narrow networks than you would expect in the beginning. Can you repeat the second question again?
So this was about the bottlenecks. So now you had the size of the network. How about the number of the number of training examples? Because if I remember correctly, your assumption was that you only consider instantiations of the network that perform a correct input-output mapping. And I would assume that with more complicated data sets, this would become also a computational bottleneck.
Yeah. So we require that this ratio, like this ratio of the number of training data samples relative to the network width, is still small. So this is one of the limits. And then actually there's a computational limit that these 4-point tensors scale with the number of training samples of times 4. So like this, the results I've shown you are for, I think, max p being 20, because then we actually hit a bit the computational bottleneck when solving the equations.
Okay, thank you very much. Any other questions from the audience?
Very beautiful work now. So this neural tangent kernel that you're using is very powerful. It's a mathematical approach to modeling what is going on, making connections to support vector machines and like kernel machines. And then, given that it's also related to a Fischer kernel, Fischer information theory, right? You can get a Kramer-Rao bound, etc. Can you now estimate generalization performance of those networks that you're doing?
That's an excellent question. This is actually what we're currently working on. Yeah.
Thanks, Ian.
Thank you. So let's thank the speaker again.